All right, the binomial theorem has a connection with the series business that we've been discussing. And so it can be written with that summation notation. We've also got this notation here that refers back to factorials, and we can say combination stuff. So you might have seen that before, again, previously, but we're going to actually do a little tinkering with that with one of our later examples. So we've got these coefficients that show up. We've got our x stuff, or from the first half of our binomial. We've got our y stuff, or stuff that comes from the second half of our binomial there, as far as our generic binomial x plus y. Turns out, though, that we've got another sort of connection here with our sequences and series as far as having like the pattern recognition idea show up when we start looking at those coefficients that appear. There's a pattern with how they're built. Now, if we're just trying to jump somewhere in the middle of a binomial, we don't want to necessarily build this entire Pascal's triangle out, especially if we have to continue completing more rows to get to whatever number it is that we're looking for. So we still want to sometimes use this combination business with the factorials to calculate out whatever number we might need. But since I've already built this out for you, and it's pretty quick to do the first couple rows, you know, it's worth having. But there is this pattern that I mentioned a moment ago. If we just have our regular binomial, we have our just regular first term and our regular second term going on there. If we take that binomial and square it, then there is a particular pattern that always shows up regardless of what our first and second terms are. There's a 1 for the coefficient, a 2 for the next coefficient, and another 1 for the third and final coefficient. So no matter what those situations are, there's this pattern to how those coefficients will always show up when we take a binomial and square it. The 2 that comes in the middle, well, from the previous row, if I take the 1 plus 1, I'll get a 2. And it turns out that that sort of pattern continues. So that what we've got going on here is we always start and we always end with a coefficient of 1. The very next coefficient that shows up and the second to last coefficient that shows up is always going to be exactly the power that I have attached to my binomial. So if my binomial has a 5th power, then the second coefficient and the second to last coefficient exactly match up with that power of 5. So there's one other pattern that's happening. And then for the rest of the entries that show up, we can say that those are going to be coming from the previous row and the entries on either side being added together. So there's that 5, just a different way of getting it. A 4 plus 6, a 6 plus 4. There's that 5 again with a different way of getting there. So if we were going to finish another row, we would start with a 1, we would end with a 1. Our second and our second to last entries would both be for that next power, which is a power of 7. If we start trying to fill in the next sorts of empty spots for the other coefficients, we would do a 6 plus a 15 plus a 20 plus a 15 plus a 6. And those would fill out those other rows if we keep going with that sort of pattern. Now we don't have to build that, because again, we can always come back to our formula here for the combination, and we can use our calculator to go ahead and bang out that calculation as well, rather than necessarily having to do it ourselves. So there is a little bit of advantage there. We don't need this for certain kinds of problems, but if we've already got it built out, it's a handy reference. And so for our first couple of examples, we'll actually use Pascal's triangle, at least the little bit of it that we've got built up so far. So as far as that binomial theorem goes, here's just a quick justification that we can match up with what we already can accomplish by actually just using FOIL. If we take a binomial and square it, well, according to these patterns that we've established, our coefficients have a 1, a 2, and a 1. According to our binomial theorem, we use those coefficients 1, 2, and 1. Each of those coefficients is also going to have stuff that's based on the first and second term of our binomial. So back to that first coefficient. It's going to only have a contribution from the first part of the binomial. So x with the full power of 2, there will be no contribution from the y. The y would have a power of 0. When we move to the next term, the power on the first part goes down, the power on the second part goes up, one at a time. Click, click. So the power on the x goes down from 2 to a 1, the power on the y goes up from a 0 to a 1. Then for the next term, power on the x goes down, power on the y goes up. Click, click. So that the x would now have a power of 0, the y would now have a power of 2. I have now maxed out my power by reaching the end there. Now maxed out my power. And so I would be done with expanding that binomial and would want to simplify each term. One other quick comment to make here, especially with these longer sorts of expansions, the powers on each of these pieces has to add up to the total power that shows up. 2 plus 0 is 2. 1 plus 1 is 2. 0 plus 2 is 2. So we have to add up to the power that appears on our binomial. So that's another little connection there that we can use, especially nice when we start talking about some of the bigger binomial expansions that we might come across. But even the next one's kind of reasonable. We can go ahead and still multiply things out. It becomes a little bit more tedious to actually multiply this out by hand using our previous algebra ways. So if we're able to step up our algebra here and start incorporating that binomial theorem with the series kind of perspective. Coefficients 1, 3, 3, 1. As far as the pieces that we've got, we have, oops, I accidentally got a y in there when I mean to have a 2. We've got an x with a full power of 3. Our second part of the binomial is the number 2, not a y. Is a 2, and it would have power of 0. 3, power of 3 plus power of 0 is power of 3. Adds up to the total power that appears on my binomial. Each of those powers, one of them goes down, the other one goes up. So on x, the power goes down from a power of 3 to a power of 2. On the number 2, the power goes up from a 0 to a 1. Power of 2 plus power of 1 gives me a power of 3. Adjust those powers again, adjust those powers again, and then we can simplify each of these terms. So the coefficient of 1, there's no extra number contribution here, so we can have our x power of 3. Our coefficient of 3 times the 2 here gives me a 6. Coefficient of 3 times 2 squared, 3 times 4 is 12. And then down at the very end, coefficient of 1 times 2 to the power of 3 gives me 8. So here's my simplified, expanded binomial, and it didn't require a lot of tedious multiplication work to get there. Let's tweak that example by just a little bit. So far, all of these binomials have had something plus something. So if we take a look at, instead, having something like an x minus 2, well, it should be very similar to this one, with the exception of having some different signs appearing along the way. So we're going to expect to get these same kinds of terms with only possibly some of them, instead of being plus, would become minus. Now here's how that's going to work. Our binomial theorem still, at the very beginning again, had referred to something plus something. So let's just real quick backtrack and look at that. Our original binomial theorem was referring to a binomial that had a plus in the middle. So anytime that we want to use that, we're going to have to sometimes rewrite our binomial. If it says x minus 2, and I need it to say x plus something, then I'm going to need to have the appropriate something as my second term of that binomial. And that would mean it would be a negative something, in this case, negative 2. Well, we're going to use the same coefficients that we just used, and we can even use that previous example as an even stronger model. We know that we're going to have all the same kinds of powers. It's just that instead of the positive 2 that shows up, instead we'd be looking at a negative 2 that shows up in its place. So if we go through and write all of that out, I'll go ahead and switch those negative 2's to a blue color here in just a moment. But going through and switching out all of those positive 2's for negative 2's would give us this sort of expression. And when we start simplifying, we'll see how the negative ends up impacting our simplified answer. So if we come to the first term, very similar again to the previous example, a negative 2 in parentheses raised to the power of 0. Power of 0 means that I'm just going to get a 1 that comes out of that. The negative is not going to impact that first term. So that first term, 1 times 1 is 1, times x to the power of 3 is x to the power of 3. In the second term, we have a negative 2 being raised to the first power. So that's just a regular negative 2 times the 3 means that we get a negative 6 in that second term with our x squared. In the third term, I have a negative being squared. Negative times a negative is a positive. Positive 4 times 3 would give me a positive 12 with my regular old x. And when I look at my third term there, I've got a negative being raised to the third power. So negative times another negative ends up being a negative. When we compare these two answers, we see that by having this negative number, or a negative second term, because we can kind of generalize that, if I have a negative second term showing up, then each of my every other term in the answer is going to have a negative instead of all of them being positive or plus. So every other term. It's a nice little pattern that you might want to take advantage of, especially if you're building the entire expansion. With Pascal's triangle that I had already worked out for you, we have the row that would match up with our power of 5. And so we can use those coefficients. Let me again backtrack, and we'll point out that specific row of the Pascal's triangle. When our power is a 5, our coefficients are 1, 5, 10, 10, 5, 1. So these are the coefficients that we're going to use for this very next example. And we're going to expand this whole thing. This has got that negative business that's showing up in there. So we're going to have that little tweak there. Let's go ahead and start out with just that quick comment about how we're going to make a quick tweak on that. We need our binomial to say x plus, and so that would mean we would have x plus a negative 3. From here, we're going to start using our binomial theorem. We're going to have our first coefficient, which was a 1, times x gets the full power, and the negative 3 gets no contribution at first. Then we always just go with plus. We always go with plus and see just how things simplify in the end. So plus, the next coefficient that we have from Pascal's triangle is a 5. Our powers, the first goes down, the second one goes up. So the power on the x drops down to a 4. The power on our negative 3 will increase from 0 to 1. Again, we also have that pattern with our exponents. The pairs of exponents will have to add up to the original power on our binomial. 4 plus 1. 4 plus 1 is 5. 5 plus 0 is 5. So we have that kind of comment that we can use as well to make sure that we're as much on target as possible. The next coefficient was a 10. So that would mean that our x would now have a power of 3, and our negative 3 would have a power of 2. Let's go ahead and save that plus sign for the next step here. Plus sign. The next coefficient is a 10. Our x would now drop down to a power of 2. Our negative 3 would now bump up to a power of 3. Our next coefficient is 5. Our x would bump down to a power of 1. Our negative 3 would bump up to a power of 4. And finally, our last coefficient is a 1. Our x would drop down to a power of 0, and our negative 3 would bump up to a power of 5. So now we would want to go through and simplify each of those. We've got 6 terms to worry about. A 1 times a 1 times an x to the power of 5. A negative 3 times a 5 times an x to the power of 4 would give us a negative or minus 15 x to the power of 4. A negative squared is positive. Positive 9 times positive 10 is a positive 90, or plus 90 times our x to the power of 3. If we remember that our negatives are now going to be alternating, we know that the next term that shows up here is going to be a minus. We can verify that here by looking at the pieces. We have a negative raised to the 3rd power, negative times a negative times a negative. So negative times a positive 10 times our x squared. Again, remembering that our signs are going to alternate back and forth, that means that the next term would be a plus. Again, that's going to be backed up by the pieces that we have. We've got a negative raised to the power of 4, negative times a negative times a negative times a negative. We actually take those in pairs. Negative times a negative is a positive. Negative times a negative is a positive. Positive times a positive. So we would have an 81 times 5 times an x. And then for our very last term, that's going to be a minus. And we would have 243 for that. One of the other things to point out at this stage, now that we've seen a few examples, is that there's another comment to make that we would want to sometimes keep in mind. This binomial has a power of 5. Our answer has 1, 2, 3, 4, 5, 6 terms total. When we expand our binomials, we always get one more term than the power that showed up. So for instance, if we had a power of 23, then the total number of terms would be one more than that, 24 total terms. That's something we might need in certain kinds of problems, but so far the examples that we've had rely on Pascal's triangle. Let's look at something that is going to rely on that combination formula that we had, so that we would have to figure out, using that combination formula or with the assistance of our calculator, what's going on here. So this has already begun, but to come back to the original problem here, we want the 7th term. So when we talk about the 7th term, we have to remember that our binomial theorem officially starts with an index of 0. So the first term corresponds to an index of 0. That means that the 7th term would, if we count it out, 0, 1, 2, 3, 4, 5, 6. So 7th term, and out loud we counted out 6 for the index. What that means for us back in our binomial theorem is that this coefficient is going to come from the combination of 17 and 6 for that index. That first term from our binomial, which is now a y, starts with the 17 and then drops back. It drops back, well, based on the index. So 17 minus 6. And the second term of our binomial is going to just automatically have that index that we figured out. So the index is 6, the power that's attached to the second part of our binomial, which is the number 2, is a 6. So we just go ahead and jump directly to that term, and we don't necessarily want to have to try to work out that many rows of Pascal's triangle and then figure out what's the coefficient of the 7th term. So we're going to just jump right there using our calculator. Now, officially speaking, as a side note, we do have that formula that connects to this. Well, that's not very neat. We have this formula that connects to this, but we also have this shorthand combination notation stuff. So we can use our calculator as long as our calculator has that combination sort of notation available to it. Let's go back and look that formula up, because I don't remember it off the top of my head quite yet. So according to that formula, we need to take the top number and do our factorial, and then the bottom has 2 factorial pieces, So up on top, we would have the 17 with our factorial. Down on the bottom, we would have our 17 minus 6 with a factorial, and our 6 with a factorial, like so. We could use our definition of factorial and work that out, or from the calculator, let me show you how you can pull up that combination business. The first thing that we're going to need to do, though, is tell the calculator that first number, which is a 17. Now we want to pull up the part of the calculator programming that's going to connect to that combination business. We're going to get there through several keystrokes here. We're going to start off by clicking the math button, and that's going to bring up some menu options. Because this combination business most often is connected with probability and statistics, we're going to have to scroll over to the probability menu, and that means that we can use our arrow buttons on the calculator, clickety, 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 click. Whoop, too far. Our third option there has that combination shorthand that we've been using when we've referred to it. So we can either use our arrow keys, or we can just type the number 3 to select that particular special part of our calculator programming. And then we need to tell it the second part of this calculation, which is the 6. Then if we hit enter, we should get that coefficient, 12,376. So, 12,376. Our y would have a power of 11. And going back over to the calculator to have that crunch out 2 power of 6 is 64. We would now need to do that 12,376 times the 64. 792,064. With a y power of 11. Let me make sure I didn't go dyslexic and write that out of order. 792,064. All right. Would have been a lot more work for us if we had tried to build out all of those rows of Pascal's triangle to get us there. Then had to count out to where that 7th term is to pull the 12,376. Well, let's not worry about that. If Pascal's triangle is not built out far enough for our purposes, let's go ahead and either use our little formula with factorials or our calculator to help us work out what those coefficients would be, so that we can go ahead and work out what it is that we needed to work out, which this time, thankfully, was only a single particular term, which is also similar to the very last example that we're going to do, but the last one, we're going to take a slightly different sort of spin. For this final example, we want to find the third to last term. This has also got a little extra quirk to it, because now this binomial is not just a plain old variable. This binomial is a 2z, as well as also now having the minus coming back into play again. So, first of all, with the more unusual nature of this question, they are not flat out telling us what term we are looking for. Not in the same way that the previous example spelled it out and said 7th term, which would mean an index of 6. Ta-da! This one's saying the third to last. Well, we don't know what the third to last one is yet. So we either have to think of how many terms we have and backtrack, or we have to think of the last index that we would use and backtrack. Let's start with the number of terms that we have. If our power is 24, then we would have a total of 25 terms. If we start at 25, then the last term is number 25. The second to last term is the 24th term. And the third to last term would be the 23rd term. Now, if we're talking about the 23rd term, the index is always one smaller than the term, so the index that we would want here would be an index of 22. Now let's just pause for a moment. This is only one way of getting to that index that we need that will allow us to build out from our binomial theorem what this third to last term looks like. Rather than just starting at the very last term number 25, the very last index corresponds to the power of 24. So we could have started there and said the last index is 24. The second to last index would be 23. And the third to last index would be 22. So we can still get that same information. So whichever way works better for you. Now that we've got the correct index, that means that we can start putting together the coefficient and the powers that we would need. As far as the coefficient, the top number is always that full power number, which in this case is 24. The bottom number is always the index, which means 22. The next part of our binomial theorem says we would need to take the first term of our binomial, which is a 2z. It would begin with the full power of 24, and then we would subtract off our index. So 24 minus, well, our index is 22. Because this binomial has a minus in the middle, the second term of our binomial itself is a negative with the 1. And the power for that second piece is the same as the index, so that's a 22. So now we can either use our formula with the factorial business and work out this coefficient, or we can switch back over to the calculator and work out that coefficient. So let's go ahead and clear things out here, start fresh. 24 is the first number. We need to bring up the combination. So we hit the math button. We move over to our probability menu. We select the combination option, which is option number 3. Then we type in the second number, which is our index number, 22, and hit enter. So our coefficient is 276. The 2z would have a simplified power of 2. We'll come back to that in just a second. A negative raised to an even power is just going to be a positive. And since that's a 1, thankfully things don't get any crazier from there. 2 squared is 4, so what we've got showing up here is 276 times a 4z squared. And so 276 times 4 is 1104. So our final answer here would be 1104 z squared. That would be our third to last term for this particular binomial expansion.